Welcome back, everyone. In this video, we're going to be talking about self-inductance. So, self-inductance is a property of some inductors. And first, we'll talk about what an inductor is and what it does in a circuit. In essence, it's just a conducting coil. And what this coil does is it resists a change in current due to an induced potential. This inductor will also store energy in its magnetic field. And what we do is we write the strength of an inductor by its inductance, which is the letter L. And this is measured in henries. So this is the circuit symbol that you will see for an inductor. Okay, remember that a resistor is a little bit different. And essentially what this represents physically is a coil of wire. So that what happens is that as current flows through this wire, if the current is changing as it does in many circuits, then that means that the magnetic flux, which is going through these coils, will also be changing. One way to think about this is just to consider one coil that has current going this way. And by the right-hand rule, if you put your thumb in the direction of that current, it will wrap around, and on the inside there will be a field that points to the right. And if you have many loops of current that do that, you'll get a strong field. So you're going to have magnetic flux. Now if you all of a sudden change that current with respect to time, then you're also going to be changing the magnetic field. The flux will be increasing going to the right. And so what the inductor does is it creates an EMF, as we've talked about before, an induced voltage that is going to be opposite. So in other words, it opposes the change in the current. And we're going to see this in what's known as self-inductance. So the inductance is a measure of how much of this back EMF it produces. And it's a typo. It should just be its coils without the apostrophe. And the equation for inductance is that the EMF is equal to negative L di dt. And this makes sense because if the current is increasing, there's going to be a back EMF that's going to point in the other direction. So we're not going to derive this equation, but from earlier in this chapter in the textbook, there was a section on mutual inductance, which we typically won't be covering. But that states that another way to describe the inductance is the number of loops times the magnetic flux divided by the current. And this suggests that Li is equal to N times the flux. Now there's also an N in this equation if you have many loops. Okay? Now if we take the time derivative of this, we'll have L di dt is equal to N d flux dt. And, sorry, this should be over N. You might notice that L di dt, well that's right here, and right here, if I put a negative sign on that, d flux dt is EMF. So this means that basically the EMF times the number of coils will be equal to negative L di dt. So that's some description of where this inductive EMF comes from. So what does a circuit look like that has an inductor? Well, you have your inductor, and then you also have a voltage source and some sort of a switch. Okay? And we're going to keep it really simple, but the question is, what happens when we first close the switch? Because initially there's no current. Okay, and this is a little bit cut off, but there's an initial voltage that goes this way. Okay, so when we first close the switch, current will flow, and that current will be very great. And the inductor is going to oppose that with an EMF, EL. So this inductive EMF is going to oppose the EMF of the battery. And what we could do is we could analyze or think about what the current in this circuit is going to be doing as a function of time. So at some time t0, when we switch on the circuit, the current jumps up. And if there was no inductor, it would go directly up to Imax, which would just be E over R of that circuit. But what the inductor does is it opposes this, and it causes the current to slowly approach that maximum current. So that is the effect of having an inductor in a circuit. Now, we're not talking about what happens with capacitors or resistors yet, but any circuit is going to have some resistance. So it's okay for us to write an R here. But this is the concept in an L circuit when we first close the switch. Okay, and then think about what happens if we then open the switch. So now what's happening is that if the switch is off, the current suddenly disappears and the flux through the inductor is becoming less. Well, the response to this is that the inductor will cause an EMF which supports what has been lost. So it's kind of cutting your losses. So if we were then to graph current versus time, we start at some initial current, I0, and at some time t0, we cut it off. Without an inductor, it would drop right down to 0. You open up the circuit and there's nothing to keep it going. So what the inductor does is it slows the descent to 0. In other words, it gives us a little bit more time to have current flowing, even if the switch is open. And so that's the nice thing about this inductor. Okay, so a very quick sample problem, and then next time we'll talk about the RL circuit. So we have a coil that has an inductance of 3 millihenries. Remember that the henry is the unit of inductance. And the way to remember this is that because we have L di dt, the negative sign is equal to EMF, then volts is equal to henries times amps per second. So that's one way to convert back and forth. Okay, so the current is going to change from 0.2 amps to 1.5 amps. So that means that di is plus 1.3 amps, and this is happening in a time of 0.200 seconds. So we want to use this information to find the magnitude of the EMF. So it's just equal to, because it's magnitude, 3 times 10 to the minus third henries, and then it's 1.3 amps over 0.2 seconds, and that's going to give us an induced EMF from the inductor of about 0.0195 volts. So it's not a lot. Okay, in the big scheme of things, this is not a huge amount of voltage if the battery is like 5 volts or 10 or whatever, but at least it gives us something. Okay, so next time we're going to look at the RL circuit, and we'll analyze how a inductor in a circuit can sort of keep the current going even with a resistor.